an adaptive bitrate controller for consistent, high-quality video streaming. This work is the result of the collaboration between University of Massachusetts Amherst, Caltech, and Amazon Prime Video. To begin with, let me give you a brief introduction of how adaptive bitrate streaming works. To prepare a content for adaptive bitrate streaming, we first partition the video stream into small segments, say 2 seconds each, and then encode the video stream into different qualities or resolutions so that the adaptive bitrate controller at the client side can dynamically select the appropriate video quality at runtime according to the varying network throughput. Let's look at a concrete runtime example. The adaptive bitrate controller, or ABR controller for short, may start by downloading at the lowest quality, say 720p. The downloaded segments are placed in a client buffer and then sent to the display for rendering. As the network condition gets better and better, the ABR controller may start downloading at higher and higher qualities. Of course, things don't always work so smoothly. Let's say the network conditions suddenly become worse, and the next segment takes too long to download before the client buffer is completely drained. At this point, the client experiences what we call a rebuffering event. You can imagine when you're watching your favorite show and a loading screen or black screen pop out. That's super annoying, right? After that, the ABR controller is likely to back off and downloading lower qualities again. From this simple example, we may get some initial sense of what are the trade-offs that an ABR controller is trying to balance. There are 3 major quality of experience components. Obviously, the users want to watch their videos at higher qualities. However, they don't want to experience rebuffering events, which is super annoying. The third point is a little bit subtle. Although ABR works by switching bitrate in accordance with network conditions, doing so too much can actually hurt the user experience by itself. This is because this leads to inconsistent video quality, and you can imagine if your picture quality fluctuates over time. In fact, by observing the data from a live sports event on Prime Video, we noticed that when the bitrates switch for more than 20% of the segment, a user is likely to abandon before watching even 10% of the stream. The problem of ABR adaptive bitrate streaming has been studied extensively in the literature before. There are 3 groups of designs. Throughput-based controllers look at the predicted network throughput and make a bitrate decision. Buffer-based controllers like BOLA or BBA look at the current buffer level and choose a bitrate accordingly. They tend to be more robust, but they also tend to switch bitrates more often. The third category, hybrid controllers, take into account both the predicted throughput and the current buffer level. Such designs include MPC, which use control theory to plan for future segments, and Pensive, which use reinforcement learning, and of course, there are many other designs. Given so many choices, a natural question you may ask is, why do we need yet another adaptive bitrate controller like SODA? I would like to argue that there are several desired properties that we want an ABR controller to hold, which is not satisfied simultaneously by any of the previous ABR controllers. First, video providers want to provide consistent, high-quality video streaming experience to all users, regardless of what devices they are using, what network connection they are on. By consistent, I mean less rebuffering and infrequent switching. It turns out that previous design usually sacrificed one in favor of the other 2 QoE components. Second, we want our ABR controller to have theoretical guarantees for all three QoE components. The closest we have from the literature is Bowler, which has theoretical guarantees for quality and rebuffering, but not bitrate switching. Third, we want our ABR controller to be robust against throughput prediction errors, which are inevitable given the diverse network conditions in the wild. And finally, we want our ABR controllers to be practical for production deployment to maximize its practical impact. Now is the time to give you a high-level overview of how SODA works. Given a predicted network throughput, SODA also tries to solve an optimization problem that minimizes over the next k time intervals. Notice it's time intervals, not next k video segments. More on this later. Anyway, it minimizes over the next k time intervals the sum of distortion costs, buffer costs, and switching costs subject to buffer dynamics and constraints. The three costs here correspond to the three QoE components. This abstract formulation by itself is not very useful because it didn't provide theoretical guarantees nor robustness guarantees. To do that, we need to transform this problem into a SIGCOMM problem to take advantage of the recent advancement in the theory community. SIGCOMM refers to smoothness optimized online convex optimization. It's essentially a traditional online convex optimization with switching costs. It turns out that to do this transformation, we need to have several modeling innovations. But just by taking the traditional formulation of ABR will not work here. I will not bore you with all the mathematical details here, but I do want you to take away two key modeling innovations we have. The first one is we pivot from the traditional segment-based view to a time-based view of adaptive bitrate streaming. Traditionally, people formulate the problem of adaptive bitrate streaming in terms of discrete segment-by-segment based process. That is a natural formulation given the segment-by-segment download nature of dash playback. However, we choose to view the video stream as a continuous fluid stream and forget about the segment boundaries for theoretical analysis purpose. This is inspired by how people analyze TCP performance. They also treat TCP stream as a fluid stream instead of discrete packets. The second modeling innovation we made is transitioning from modeling rebuffering time directly to modeling buffer stability instead. Because there's a QoE component called rebuffering time, people intuitively try to model rebuffering time directly. As you can see in the figure shown here, there are two problems with this. One is that even if the buffer level is dangerously close to zero, there is no penalty whatsoever because the controller thinks there's no rebuffering. The second is that this formulation is more like a hard constraint, which is not directly optimizable. To overcome this, we choose to model buffer stability instead. So we have a target buffer level, and we impose more and more penalty as the buffer level drops below the target. This way, the objective function becomes smooth, and the algorithm turns out to be more robust in practice. With these modeling innovations, we successfully transformed our ABR problem to a SIGCOMM problem, and we can say some nice properties about how a SODA will behave in practice. In particular, we can theoretically show that SODA satisfied exponentially decaying perturbation property. Let me help you understand this by walking you through an illustration. Let's say the black line here is the optimal trajectory of an AVR controller. Each of these labels are states. You can think of it as the buffer level and the bitrate. At each point, when Soda makes a decision, it may make a mistake because of super prediction errors or other factors, which is inevitable. However, what's nice about Soda is that we can theoretically prove that the impact of each mistake will decay exponentially into the future. In other words, the effects of the mistakes will never accumulate. This is in contrast to other systems where one mistake may cause cascading effect into the future. As you can see, the trajectory of Soda will not deviate from the optimal trajectory too much. In fact, we have a theorem stating that the total cost incurred by Soda divided by the total cost incurred by the offline optimal algorithm is 1 plus big O rho to the k, where rho is a factor smaller than 1 and k is the lookout window length. Note that a ratio of 1 essentially means an algorithm is optimal. Here is an exponential decaying factor, meaning that the performance of Soda will converge to the offline optimal as the lookout window increase exponentially fast. In fact, we have another theorem precisely quantifying the performance of Soda in relationship to the magnitude of the prediction error. But that is a bit more technical, so I will refer you to our paper for more technical details. Now, what's great about Soda is just that not only does it have some theoretical guarantees and interesting theoretical properties, but also it does perform well in practice. We first implemented a prototype in browser and conducted emulations on Puffer, which is an open AVR research platform. We compare Soda with a bunch of state-of-the-art baselines. What we find that is Soda achieves the highest overall quality of experience by a significant margin compared to other baselines. In particular, it does so by achieving a reasonable quality, a very low rebuffering ratio, and very low switching rates. Inspired by the great performance we see from the prototype evaluation, we decided to try it out in production. But before that, we need to make Soda practical for it to be able to run in the wild. By practical, I specifically mean it has to run fast, given there are some very low-end devices in a production environment. So Soda has to be efficient. Recall that Soda is trying to solve an optimization problem over the next few time intervals. So to do that, the naive thing to do is you enumerate over all combinations, which is their exponential amount of them. So brute force or a solver, just a commercial solver, is obviously a no-go in practice. Some researchers proposed table lookup before, but that is not scalable and will incur high operation overhead. Now, through theoretical analysis, we discovered that for Soda, we only need to consider monotonic bitrate sequence. And monotonic, I mean, it's either increasing like this or decreasing. This translates to only less than 150 iterations in practice, which is not a big deal even for low-end devices. Next, we take Soda to the production network on Prime Video. We try it out for users in more than 10 countries and for some large live events, sports events. The interesting thing I want you to notice here is that Soda reduces the bitrate switching by almost 80% compared to a well-tuned production baseline. Think about it. It's 80%, a huge and dramatic improvement in terms of user experience. And what's more important is that it does so without sacrificing the other quality of experience components. It has slightly higher mean bitrate, and it has lower rebuffering ratio. Another takeaway from the production deployment is that SODA can successfully run even on low-end devices like set-top boxes. And SODA achieves this amazing performance without relying on any sophisticated super predictors. In fact, we just use the simple sliding window predictor and that's it. Finally, to summarize, with time-based and buffer stability modeling, we can provide theoretical guarantees for SODA using smoothness-optimized convex optimization framework. SODA is highly performant, robust against prediction errors, and practical. We believe the theoretical insight behind SODA, in particular the exponential decay perturbation property, can be potentially transferred to other networking domains. In fact, as you may imagine, the exponentially decaying perturbation property is a very nice property to have even for other network systems, meaning the effects of errors do not accumulate into the future. That concludes my presentation. Thank you very much.